Hi and welcome back to the lab. And today here on the bench we have a tiny Yaesu FTM10. So that is a very rare UHF and VHF radio, and the radio won't receive on 70 centimeter and on 2 meter. So let's see what we can do for that tiny radio here. Okay, and here is our tiny radio FTM10, as we can see. And I've already connected it to my power supply, and you see it is already consuming 5 milliamps, so that is a standby current, so something is already going on. Okay, so let me switch the radio on. Okay. Okay, so we already hear static, which is good. Let me set here the 2 meter band to what I have dialed in my my tester. So I'm on 525, so nothing so far. Yeah, so the view is a little bit difficult here on our display, but let's try to do it this way. Alright, so yeah, I have switched off here my speaker because everything is connected to the radio. I'm feeding the radio with minus 93 dBm, which should be an S9 level on, you know, an VHF radio or UHF radio. But I do not hear nothing, not even a bit. But let me go over to our tester so that you can see the figures. Okay, so let's see what we have. So we have also static here, and we see we are feeding in with minus 93, and we see nothing. First of all, I mean, we need to check 70 centimeters, of course, as well. But first, let's try the following. Let me increase our level here to, let's see if something happens. Can you hear that? And watch the signet. So we see with minus 73, it is also very, very noisy, but there is a signal which is finally a good sign. All right, going back here to our radio. I'm a little bit confused because it is not showing any S-meter signal, so maybe I have to increase it a little bit more. I mean, it is already telling us a lot, so we know that you know, the front end, the mixer, the PLL, and so forth and so forth is obviously working. So audio amplifier and what have we. So the signal path at least is somehow working. Even we have here maximum reduced sensitivity. So that is what it is, what we see here on the first glance. So let me increase the signal even a little bit more, so you may hear. So try to listen to the speakers, so in the background you still hear the noise. Now let me increase it here. Yeah, so I do not really get the noise away. Let me switch it off because it is annoying. But on the other hand, there is no S signal at all. So I'm feeding now with minus 73. That is quite a lot. Wow. Okay, so let's switch over to the 70 centimeter band. Okay, so let's go to 439.050. So let me dial in that frequency. Okay, and then back at minus 93 dBm. We have only static, so let me increase the level. It is coming out of the noise. So that is minus 73. So that is already a shortwave S9, and you hear a lot of noise. So that means on 70 centimeters we have definitely the same problem, and we have no S meter, nothing. Okay, so now where to start, and I have looked here a little bit through the owner's manual, and I found, how can I show it, that there is something called band expansion. And so I have different sections, and let's see if this radio does have these different sections. And I've aligned it here a little bit. And so you see we have FM radio, so AM, and weather channel, and air channel, or band. It is band, it is not channel, it is air band, of course. And we have GR1. And I'm now curious, and of course we have GR2, which is 350 megahertz, but let's go here with 174, and let me dial in 174, because I believe, so you have a different filter width normally in any radio, and well, our normal, let me say here in Europe, our 2-meter band, so that is something 145. So there is a filter normally in between and is filtering these signals, right? So now if we choose another band, then maybe it is not the same filter set, and we check it in a sec here in our block diagram. But first, let me simply check what happens if we dial in 174, what I have prepared now on my tester. Let's see what happens. Oh, let me switch in the speaker, and something that is annoying once again. Come on, 174 can't be so difficult. And that, what is, hey, have a look. So let me do you hear that? And look here, suddenly we have S meter display. So that is really, really curious. Or maybe not. We will find out. Okay, so watch our tester. So I've dialed in negative 93 dBm, and look here, a really nice synod, so that is fine. And now let us simply reduce our input level here. Let us reduce it, and let's see what it is doing here. And you see I can go down with our input level, and now it is slowly dropping. So that means obviously our GR1 band is working. So obviously, with poking around a little bit, we have gathered already a lot of information which helps to find a good starting point. And the most important information we got from this year is that we have an S meter reading. Why is that so important? Very easy. So you need, a signal or a voltage level to finally display an S meter level. And very, very often in many radios, the AGC signal, so the automatic gain control, is used for it. And so I believe where we should start looking for the problem is where our AGC gets produced. So let's go into our schematic. Okay, so that is our schematic. So very scaring maybe, but don't get confused. So even our block diagram, which is this here, is more or less the same complexity. So, well, generally spoken, we have some sections where we need to look after, and that means here our front end. Somewhere here we have definitely our mixers, and we will have our filters and so forth. And then we come here into a ship, and we do not need it closer in the moment. So we will here have a mixer, and then our FM demodulation chip, which is here, and then it goes over until the audio amplifier, and then we have here our speaker. So that is briefly our signal path, all right? So therefore it is not much more complicated here in the real schematic. So what we see here, and I hope you can already read it. Let me double check. So we have here the different sections. So you see here, for instance, 400 up to 550 megahertz. So that is obviously our 70 centimeter band. And you see here we have, what was it called? GR2, I believe, 300 Mac 2, 399. And then you find 108 to 199, which is our 2-meter band. And within this band here, you find as well what we found as GR1, okay, and our normal 2-meter band. Both is covered by this front end here. And you see we have here our front end transistor, and we have here our first mixer. And because on GR1, I believe it was 174 megahertz, it was working fine. So that means this all here seems to work without any problem, okay? So that then means if we go up here, we see here our first filter, okay, after the mixer. So frequencies are not so important in the moment, but that is our first filter, somewhat 40 megahertz, I believe. We can easily find it here. I hope we get here a better information on the frequency. Yes, we can. So that here, 47.25, that is our IF filter. And you see directly behind the filter, we have the IF amp. And what you see here, by the way, AGC. Okay. And the question here, of course, is where get the IGC produced. So that is something we need to find out. But let's go back into the schematic. And yes, so we have here the filter. What was it? 4725 megahertz here. And that here, our Q1407, that is our IF filter, okay? And then you see always we have here our switching diodes, which needs to get biased. And you see we approaching here our Q1408, and the Q1408 is a mixer, and it is obviously our FM discriminator, so the FM demodulation, maybe AM as well, not entirely sure. How do we know? Because we find down here our crystal filter, so the CF1402, so that is a 450 kilohertz filter. So that means within this chip, NJM2552, so that is a lot of things are happening in this chip. And I wonder if this chip, and that is what I believe, that the AGC gets finally produced. Can we call it that way here in our Q1408? But let us double check. And here's the data sheet, and you see 100 megahertz input mixer and 450 kilohertz FM and AM IF demodulator IC. So that is what I expected. And yeah, look here. So we have here our incoming frequency. Here is a mixer. So we have here another oscillator, and that gets then mixed down to 450 kilohertz, goes here out, our mixer out, goes in here, I don't know, I'm AFM, FM, IFM is here. So I believe between 3 and, what is it, 8? No, 7, there must be, or I believe there is our filter. And then you see that we have then here another mixer. So that is here the quad demodulator, FM detector, whatever you want to call it. And then at pin 11, we have our FM audio frequency out. So that is what we need to know. And let me check. Look here. And we have our RF RGC output. Okay. And let me see if, what is it, pin 17. Let me check if we get some more information on pin 17. Look here. So that means output of RF AGC circuit. Pin 70 outputs a DC voltage to control the gain of external RF amplifier. So that is a signal which get used to regulate our front-end transistors and maybe the IF transistor. Let's go back to what we have. We need to analyze it a little bit more, but what we can say, pin 17, which is here, goes, I don't know where it goes to. What is it here? So that is somehow our AGC. And where is it going to? Let us follow it. Yes, it is controlling. As you can see here, the first gate of our double gate. This is our VHF front end amplifier. And so the voltage is controlling here the gate, and that means that is our AGC. So now we know how that is working. And going back here, you see between pin 3 and pin 7 and 5. 5 was 5 AM, maybe, not sure if it was AM. However, we have here our filter in between, and then we have the mixing, and that means we have here our AF output. So that means, because we do not see our S meter on our normal, so something should be mentioned here as well. Look here, yes. So that is very nicely made. So somehow all schematics are somewhat similar, but what we can see here, so you read normal on this line, so that is definitely coming from the processor, and you see that is going here to the digital transistor. And if that is going low, then we get power or voltage supplied to, where is it going? Yeah, very nice. Look here. So it is going here to our IF transistor, which amplifies the output of our filter, 47.25 megahertz. And so that is a normal operation. And then I've seen we have here also a wide. That means we have a more wider filter, whereby this is then obviously more narrow, so that is more for the normal frequencies we are using here. Okay, so you see that with the wide signal which comes from our processor, so that's low obviously because that's a PNP digital transistor, and you see that is then, where is that going to? Let me double check. Look here, here's another filter, by the way, a 10.7 megahertz filter, and that is here also amplification. Where is it coming from? Look here, look here. So we have the same input, so that is obviously over our 40.7 megahertz filter IF, and then it goes into pin 20, so that is the input, and obviously we have a second pass, and that goes over this amplifiers here, and there must be another mixer somewhere here, because we have here a different filter to that, so that is 47.25, and that claims to be 10.7. okay, so that means look here, so we get here obviously 11.7 megahertz, so that is obviously a mixer which is somehow feed here in this both transistors. So I believe this must be a mix, I believe, or this is a mixer, anyways, doesn't matter. So then we have an IF of 10.7, and that then goes to the same input of our IC. So we have two different signal passes. And what does that mean? Look here, so that is important as well. So that is our normal supply transistor, and you see that it is not only going here to our IF transistor, so it is also going here over this R1868 to bias this both diodes in order to be able to let the signal through. So our 450 kilohertz signal, okay, and when we have it on wide operation, this transistor here is delivering, and you see suddenly we have here two diodes, and the funny thing is obviously here is no filter, so it is wide, it is very wide, so we get here our IF frequency out, and you see it is without filter, directly feed in, and okay, now I understand why our 174 megahertz is working fine, whereby our normal frequency, our 145 whatever, is not working, because we have two different passes here through our IC, and since we do not have our S meter working, which is definitely somehow reproduced here out of our AGC signal, because that is simply a DC, all right? And that means that we need to start looking for what we have. We need to start looking around our Q1408. And I hope you got the point here with all this analysis. So this here by its own, so our S meter gave us a hint where we should start looking, and then we analyzed a little bit the circuitry, and now I know exactly where I can start probing. So I hope you got this point, that it is really crucial to understand what's going on, and you always need to look to everything to gather all this informations to get a starting point first for your analysis, and secondly, where you start probing, okay? Now, next step is I have to open our radio. Okay, so let's start here. So that is funny. Is it only a little service hatch? Or what is it? So let's see. So as I said, this radio is somewhat rare. I'm not sure if I have ever had this radio on the bench. Yeah, it is a service hatch, but we cannot really get to everything we need. So therefore, let us take off everything here on the bottom and let's see what we have and where we find our components. Okay, so let's see. Here we are. Very nice. A lot of components. So yeah, so we have definitely here a kind of filter. So that seems to be the processor. Here we have some regulators and so forth and so forth. So this here looks like our transmitter final stage, and yeah, voltage regulators here, most likely here. Do not exactly know what that is. We need to check that. Here that is most likely the crystal for our processor. Yeah, so let us analyze and let's find out where our Q14OA is. Okay, so I have already analyzed where the chips are, and down here we have our Q14OA08. So that is our FM demodulator and mixer and so forth. What I found as well is I need to go closer a little bit. So the filter is from, so that is only the soldered joints here on this side, but you see 1, 2, 3, 4, 5. So that is the filter, and what we can see here, that obviously somehow the signal gets here from pin 3, yeah, to the filter and so forth. The first, what I want really to know, because you may hear in the background, so that is our tone on 174 megahertz, so where our radio is perfectly working. And what I want to know, if we get on pin 17, so what we have seen before, our AGC DC. So let's do that first. Okay, so I've tried to put it here all to a place where we can see everything. Again, we are still on 174 megahertz, and of course we have receive, as you may hear, without any noise in the background, because we have a SINAT of approximately 40, 38, 39. Anyways, so what I want to see is if we have at pin 17, do we have our AGC? Oops, that was a clip. And you know, that is always a shocking moment. Okay, so let's see that we can get everything here. So that is there. Okay, so we see 1.5 volt. Important now is what happens if I reduce our level. So I'm on minus 90 dBm and I'm going down. And yes, so what you see, we decreasing our AGC voltage as well. And that is a clear proof that that is our AGC output, which can be used as well for the S meter. So now let me switch over the radio back to 140 whatever, and let's check if we then have our AGC as well. Okay, so you see that the radio is set to 145.525, and when we go over to the tester, you see exactly the same. So 145.525, and we do not have a signal at all, only noise. So now let me go a little bit higher so that we can hear something. Yeah, okay, and we are at 67, which is already a big signal. And let me double check that we can see everything. And let me go back to the same test point. Do we have AGC? Oop, I can't see it really. It is here. That is a test point. Oh wow, I have only 88 millivolt. So what happens if I increase the signal? Almost nothing. Almost nothing. So that is proving that it has something to do with the AGC, which gets not produced, and that then subsequently won't show up on the S meter. So that is now very clear that this idea was right. All right, and what I now want to know is if there is maybe something wrong here with our 47.25 megahertz filter, or maybe with the little IF amp, which is, I've just looked it up on the PCB plan. I believe this one here is our little IF transistor. Let me go a little bit closer. So this seems to be the IF transistor. This is our filter, and at pin 20, so up here, there we get our IF signal, so the amplified IF signal into it, and then everything gets converted here in the IC over our filter, which is down below, and gets out. And I just want to know if this signal path is working correctly. So let's start here at, let's say at the input, to see what is the input, what is the output, what is our amplifier doing, what happens when it gets converted, so to 450 kilohertz. Let's see if we find this signal here at our IC, and then let's check the input to our filter, and then let's check the output of our filter, then the input here back into our IC, and then let's check finally the audio, which gets of course out of our filter as well. So that is what I've planned to do, and of course we use therefore here our probe from our spectrum analyzer, and we go step to step. So we start here, there, and then we go into the 450 kilohertz area to go ahead and follow along. So what you already can see, we have set our center to 47,250. So that is exactly our IF frequency, and let's check what we see. Okay, so let's start probing. I'm going to probe at the input of our filter, which is here. Okay, so we still have modulation on. So let me switch off the modulation, that we have a clear signal, and let me put the peak for a marker for testing. So you see the 47,250 megahertz, so that is right, and we are here at minus, what is it, 45 dBm. So that is at the input. Now let me check the same signal at the output to see if the filter is fine. Let me check where it is. It is here, 46. So that means we have approximately 1 dB loss over the filter, which is totally fine. So the filter is good. So now let me go to the IF transistor, which is, where is it? The 14Q1406. 1407. Okay, got it. So now let me go down to that transistor, and we expect, of course, an amplification, and minus 33, which is, from my point of view, more than fine. Okay, so transistor is working. Now let's see what we have at the input of our IC. Let me double check where we are. I believe it is here. Yeah, so minus 33. So that is approximately the same what we have at the input. So that all looks fine. Now, of course, we need now to change over to the 450 kilohertz. So therefore, let me change the center setting to 450K, which we have. You can see it again down here. Now we are at 450, which is the intermediate, and that is here behind our IC. Let me see, where is our input? Okay, so there we have a signal, which is, let me peak search our marker. You can see it 450, and it is minus 21. There you can see it. And okay, that is the input. Let us check the same signal at the output of our filter. Where is the output? Let me go over to the output, and what do we have here? 53. Ah, come on, what is that? Look here. So again, that is our input. So that is negative 22. And we have here our output, which is 53. So that is 30 dB loss. So that looks 22, 50, let me again, negative 50, yes. So that is 30 dB loss. That is not okay. So maybe our filter is defect, but maybe let us check the diodes. Okay, so what have we done? So we have, once again, to repeat it, we have tested input-output of the filter. We have tested our IF transistor, which all was fine. And we tested our input, which was fine as well. And our output here on the 450 kilohertz level. So we have seen here that at the input of our filter, we have minus 22, I believe. And then we tested at the output of our filter, and that was, and I tested to be precise, I've tested here at pin 7, and we have seen that, you know, it was minus 53, which is a loss here over this pass of 30 dB, and that would explain our problem, because then the input is much too low. But what I want to check first is if here our diodes are working. So we get, as we have seen it before, here the voltage which goes here over our resistor, and then we have here the bias for our diodes, because otherwise they wouldn't let the signal through. Now I just wanted to check if everything is fine here with the supply of the DC for biasing our diodes. Okay, so now let's test if the diodes are getting biased. First we start with the supply voltage, which comes over the R1868, and the 1868 must be where is it? It is so tiny. Okay, 8.8, so that is good. That is the input. Let me look behind that, and it's 6.6, which is still fine. Now that is then already the input of R1443, and that is here, this guy here. Oh, come on. It is so tiny. 6.7, that is fine. And now behind that resistor, 6.7. Oops. So come on here. Where is my resistor? There. So that is fine. And now we can directly test the diode, the D1406, which is, where is it? I can't really see it. 1406. 1406 must be this guy here. So that is the input here. Come on. That must be the input after the resistor, which is fine. And now on the other side, on cathode, 3 volt, input was 3.5, so that is a voltage drop of approximately 0.5 of a volt. So that means this diode is perfectly biased. And now we do exactly the same on the other side. At the D1408, which is, where is it here? I believe, so that is the anode. Let's double check. Where is it? 1408. Where is the anode? Let me check. We get voltage on the anode. And let me check, where is the anode? Here's the anode. There is no voltage. That is funny. So let me check the resistor, which is a 42, and that is exactly the guy down here. So on this side there is no voltage. What's going on here? What is here on the input of that resistor, which is, oh come on. Oh, that's looking good. 6.6, so that is the same what we have on the other side. And here, nothing. So that means, oh, that means something is wrong. Okay, so what have we tested? So we tested from here with approximately 9 volt, 6.7 here, 6.7, and here we have the voltage drop of about 0.5 of a volt. And that means this diode down here to ground is biased just fine. Then we have checked the same, and we found that at the anode side we have no voltage, whereby we have the same voltage at the input, which is here and here exactly the same, but then suddenly here no volt. And that means that most likely there is somewhere a short, because something is pulling down our voltage to ground. And well, let us check what's going on here with our filter. Okay, so let me switch over to ohm. Let me completely switch off the unit so it is not under power any longer. And I just want to know, I mean, we have ground connected here, and I just want to know what is the filter resistance to ground. 12 ohm. Okay, let us check at the input, which is here. And okay, so you see at the input we have 43 kilo ohm, all right? And at the output of our filter we have only 12 ohm. So that is, yeah, that is almost completely dead short. So, and that is pulling down our voltage. So I believe that we have a problem with our filter. What we can do else is we could check the diode, and therefore let me check if we can do that. We go down here directly. Can I see it? It is a little bit difficult here. Let me check the diode, which is here. So no, diode is fine. So 0.5 of a volt, or almost 0.6 of a volt. that is definitely fine. So the diode is not the problem. I am for, let me say, 95% sure that we have a problem with our 450 kilohertz filter. So that would explain everything here. Okay, what does it mean? I mean, again, our filter is down here. So we have to take out the PCB completely. By the way, so, oops, that is focus. Come on, focus. Hey, come on. So you can see here, that is the diode, which were fine, but from here to the output of our filter was 12 ohm, whereby the input was 43 kilo. And that means, I mean, these filters are a little bit known for making trouble sometimes. So we have swapped out many in, for example, FT8047 and so forth. So that is a known problem with those filters, but normally you hear first that you know, they have a crispling sound and such, but here it seems that it went short, and you know, it was almost not possible to receive something. So okay, next step, let's take out the board and then we go ahead. Okay, and here's our board out of the chassis, of course, right? And well, when I now flip it over, we find our filter down there. And now, if we would have seen the filter earlier, so look around. So that is exactly what we find on filters which are developing this problem. So you have this, I do not exactly know what it is, like crystals, and yeah, looks like white dots here on our filter, but that is the clear sign for those filters to be failing, and that is exactly what we can see now. And once again, if it would have not been in here our circuit like upside down, then it would have been directly clear what our problem is. But anyways, no problem, we had no issue with testing it out. Now it is a little bit difficult to get here this white, I don't know what it is, and I believe that there are, so look here, there are obviously some components as well under this kind of glue, and now that will be a challenge to get the filter out of the PCB without damaging anything. Wow. Okay, so I've cut it around with a sharp knife here around the filter, and I have already, as you can see, desoldered the joints here, and everything looks quite nice. So those filters, desoldering those filters are always a little bit tricky, but now let's see if I can move the filter out. It feels good, so yes, very nice. So here is our filter. Important is to see that it is M50, so for 450 kilohertz, and that is important. Foxtrot whiskey, because that is declaring the filter width. So you really need to put the same filter width back into the circuit, otherwise it wouldn't really work. So take care on that. Alright, and what you can see here, so I have cleaned everything here around our PCB. Everything of this white sticky stuff is gone. And now, okay, so here is our old filter for sure. And I have grabbed already here a new filter out of my box, so that is here. And now it is very easy. We have to put it back and then we go on. Okay, so our new filter is in, but we are interested in the testing. So just remember, let me see if we can get it both in here. Remember that we tested from the output of our filter to ground approximately, what was it, 12 ohms. So that means here is our output pin, okay? And now let me here use somehow a ground point, maybe there, and you can see we have approximately 30 kilo ohms. So that means the ground short is gone, and that here was our input. And now you see it is approximately the same, 29. And where is the other pin here? And that is 29 kilo. So that means our other pin here, our other filter, our old one, which is down here. Let me check if we can reproduce it here as well. Let's check. Let's check. That is the output. Let's see. No, not really. Not really. Ah, our 12 ohm. Look here. So there we have our 12 ohm once again. And on the input we do exactly the same. Come on. Can I read something? And you see that is now not in circuit. And that means that we have even a higher resistor of 7.8 meg, and that is normal. So that is a proof that we have really a shorted filter here. Right, and the next step is, of course, we have to put it back in our housing. All right, and everything is back, and all connections are ready for testing. So, okay, let's try if it works. So, okay, so of course we need here some ground. Everything else is connected, and we need some positive 30.8. And we see we have our 5 milliamps, so that is just fine. Okay, so let's see what happens when we start it. Okay, so that is our 174, which we tested on before and where it was good. And let's set it to, let's say, what? Oh, what's that? Well, we have already our S-meter back, but we do not hear anything. Let's go over to the tester. Okay, and here we are, and we are on the right frequency, because otherwise we wouldn't see our S-meter. So that is above S9 level, but we do not have audio, and I see why, of course. So that is still switched out while we were testing with our spectrum analyzer. Ah, our audio is back, and look here. So we have a sign out of 40 dB. And that is fantastic. But of course, we want to know if we have the sensitivity back. And well, let's see if you can see it. Here is the overview, 140 up to 150. And we expect to see 0.2 microvolt for 12 dB sign out. So let's see if that works. Okay, so therefore we have to go over here, and we want to reduce, of course, now our input signal. And I mean, clear, you see a crisp, clean sign here. Let's go down. Okay, and let's switch it to microvolt, because we have seen in our specs we expect 0.2. So that means we still have to go lower, but you see we have still a very nice sign out, and it should not drop under 12. So that is a specification. And let's go, I'm already a little bit too low. Let's go to exactly 200 point 200, so 200 nanovolt. That is what it is. And look here, so that is 17, 15, 17. So of course we are in the noise and you can hear it, but the sensitivity, the specified sensitivity is given. So let me go over to 70 centimeter, and the last frequency we had dialed in here was 43905, and we are still on 0.2 micro, so 200 nanovolt, and you see, so we are above specification. That means the radio, as it is here, is better than spec. And what you see as well, so our S meter is gone, and that is because the signal is so low. Let me simply go up and you directly see that it is coming back. All right, so that means our radio is fixed, and it can go back, of course. I do not need to show you that I have to put back here our plate here, and for sure we have put here some heat grease where it was necessary, so everything has been done properly, and you see now it is working perfect. So that's it for the day. Hope you learned something, and catch you next time. Bye.